For thousands of years, every blacksmith has known one fundamental truth. If you want to shape metal, you have to get it hot. Heat softens the bonds between atoms, turning a rigid steel bar into something as pliable as clay. But researchers at Northwestern University recently discovered something that defies this ancient logic. Under extreme ballistic conditions, the rules of thermodynamics seem to flip on their head. They found that when you hit certain metals fast enough, we're talking kilometers per second, the heat generated doesn't make the metal softer. It actually makes it significantly harder than it was before the impact.
To understand why this is so strange, we have to look at how metal usually fails. Normally, when a piece of copper or aluminum is struck, the energy of the impact turns into heat, which allows the internal structure to slide and deform. This is why a bullet hole in a steel plate looks like splashed liquid. The metal literally flowed away from the point of impact because it couldn't maintain its crystalline integrity under that much stress and heat. But in the Northwestern experiments, the metal didn't flow. Instead, it braced itself. It's a phenomenon that challenges our entire understanding of high-speed material science.
The team used a specialized laser-induced particle impact test. They fired tiny metallic spheres, just micrometers wide, at a target at speeds that would make a fighter jet look like it's standing still. At these velocities, the impact happens in a millionth of a second. There is no time for the heat to dissipate. It's an isolated, violent event where the physics of the small scale take over. The researchers expected the metal to turn into a soft mush at the impact site. Instead, they found the crater was shallower and the material was denser than any traditional model predicted. This isn't just a minor curiosity. It's a complete reversal of what we call strain rate effects. Usually, the faster you deform something, the more it resists, until the heat builds up enough to melt it. But here, the heat and the speed are working together in a way we've never seen in pure metals. It's as if the metal is learning how to be stronger the harder it is hit. To find out how this is possible, we have to look past the surface and dive into the world of dislocations, the tiny flaws that determine the fate of every machine we build. The secret lies in a concept called dislocation density. In normal metal, these dislocations move around like people in a hallway, allowing the metal to bend and change shape. But when the impact speed crosses a certain threshold, something happens that prevents this movement entirely. The hallway doesn't just get crowded, it jams shut. This jamming is the key to the paradox, and the physics behind it is as brilliant as it is unexpected. Let's look at what's actually happening to those atoms in that millionth of a second. Inside every piece of metal is a crystal lattice, a perfectly organized grid of atoms. But no grid is perfect. There are always tiny line defects called dislocations, where the roads don't quite line up. When you bend a paperclip, you aren't stretching the atoms. You're moving these dislocations through the metal. It's like a wrinkle in a rug. It's much easier to push the wrinkle across the floor than to move the whole rug at once. This movement is what makes metals ductile, or soft. As long as dislocations can move, the metal can deform without breaking. But dislocations have a speed limit. That speed limit is roughly the speed of sound within the material. If you try to force the metal to change shape faster than its dislocations can migrate, the system starts to break down. In the Northwestern experiment, the impact was so fast that the dislocation simply couldn't move out of the way. Imagine 1,000 people trying to sprint through a single exit at once. Nobody gets through. Because they can't move, they pile up. This is called work hardening, but on a scale and at a speed that was previously thought to be impossible for pure metals. Here's where the heat part of the paradox comes in. Usually, heat gives atoms the energy to vibrate and jump around, which helps dislocations move more easily. This is why heat usually softens metal. But during a ballistic impact, the heat is generated so quickly that it doesn't have time to spread. It stays trapped at the site of the impact, creating a localized zone of extreme energy. In this specific sweet spot of speed and temperature, the heat actually helps create more dislocations rather than helping the existing ones move. You're essentially flooding the hallway with more people while the doors are still locked. The result is a material that is literally too crowded to deform. The atoms are locked in place by their own chaotic density. The metal becomes a nanocrystalline structure in the blink of an eye. This new structure is incredibly strong. By the time the impact energy is finished, the metal at the strike point has been transformed into a version of itself that is harder than the original material. Think of it like non-Newtonian fluid, like oobleck. If you touch it slowly, it's soft. If you hit it hard, it turns into a solid. This is the metallic equivalent, happening at the atomic level. This discovery at Northwestern didn't just happen by accident. It required a new way of looking at microballistics. using lasers to simulate the conditions of a meteorite strike or a high-velocity fragment. By capturing these events at the nanosecond scale, researchers are finally seeing the hidden physics that traditional engineering models missed for decades. And now that we know the heat-hardening paradox is real, we can start to use it. We can design materials that don't just survive punishment, they thrive on it. The most immediate application for this physics is in space. Low Earth orbit is a shooting gallery of debris traveling at 7 kilometers per second. At those speeds, even a fleck of paint can hit with the force of a grenade. Current spacecraft use Whipple shields, layers of metal designed to break up the projectile. But what if the hull itself got stronger every time it was hit? By using metals that exhibit the heat-hardening paradox, we could build lighter, thinner hulls that actually become more impenetrable as the mission goes on. This isn't just for space. On Earth, this could revolutionize ballistic protection. Modern body armor relies on ceramics that shatter to absorb energy. They are one-and-done systems. A heat-hardening metallic shield could potentially take multiple hits in the same spot, with each impact forging a harder plug of material that makes the next penetration even more difficult. It changes the engineering philosophy from how do we stop the damage to how do we use the damage to our advantage. We could even see this in manufacturing. Imagine a ballistic forging process where instead of slow presses, we use high-speed micro-impacts to create components with surface hardness that rivals diamond. This would allow us to use cheap, abundant metals like pure copper or aluminum and give them the properties of expensive, heavy superalloys just by treating the surface with speed. It's a way to hack the periodic table, using physics to bypass the natural limitations of the elements. The researchers are now looking into how this effect works in alloys and more complex materials. If pure metals can do this, the potential for engineered composites is staggering. We are entering an era where materials are no longer static. They are dynamic systems that respond to their environment in real time. It's the ultimate realization of what doesn't kill you makes you stronger, applied to the very atoms that make up our world. Next time you see a shooting star or a high-speed jet, think about the invisible war happening at the atomic level. The faster things go, the more the old rules of soft and hard begin to blur. The heat-hardening paradox is a reminder that even in a field as old as metallurgy, there are still profound secrets waiting to be hit hard enough to reveal themselves. We used to fear the heat and the speed. Now we're learning to use them to build a future that is truly unbreakable.